and probably I'm doing my project in cosmology. So yeah, and this is something which I like. I like to read a lot, so I just read it and I just wanted to discuss it with you. Maybe I can get a good hold of this subject myself, and also maybe I can share some knowledge which I've been learning. So I'll begin with the simple principle of the simple Einstein special theory of relativity. As we all know that it deals with the basic two phenomena that all the inertial reference frames are equivalent, and there is a constant and there is a velocity limit in the nature. Uh, Velocity limit in the nature, which is well known to be speed of light c. Okay. Earlier there was Lorentz, who has found himself the transformations which, like, this is way before the Einstein presented his special theory of relativity in 1905. So it's like a year or 2 years earlier than the Einstein presentations. Then the Lorentz found these transformations under which the Maxwell equation don't change their forms. It's like they are the same in the both the transformations, like a mathematical transformation, but he didn't present any physical meaning of these transformations. So there comes the Einstein saying that, okay, no, I can write the simple transformations which the Lorentz has written. Just take this simple form. Now we all know that these are the transformations between the two reference frames, in which one frame is at rest and another frame is moving with the velocity v related to the rest frame, and another how the time and the spatial components are related in two different frames. And here we have the velocity only in the x direction, so the transformation will leave the y and the z component invariant. So this is just the basic Einstein special theory of relativity. Now we'll go a step further in dealing with the general principles. Einstein was concerned that in the about transformation we only have the velocity that one frame is going with a constant velocity related to another frame. But there are also more questions that if one frame is accelerating with respect to another frame, and how we're going to be deal in that situation. So the Einstein presented a simple formula, the principle of equivalence. Okay, let's spelling all this. In which he employs the two basic phenomena, the Newton's second law of motion, which says that if we are applying force to any mass, then the formula for the acceleration can be acceleration, and the relation between the force and the acceleration is given by this simple phenomena. Here the mi represents the inertial mass. Inertial mass is just the resisting force of any resisting mass for any, like, if we are applying a force to an object, how the resistive mass is, like, is the intrinsic property of the mass. And also we have a simple formula also, that if we have a free falling mass in the gravitational field, and how does the gravitational force act on that mass. Here the mg can be understood as a simple coupling constant between the mass and the gravitational field. So if we have a so I can see that the forces are same, so I can pretty much see a much cancellation, and I can say that, okay, if the acceleration is equal to the gravitational acceleration, then mi must be equal to mg. It's just the basic. I can see from the above equation that, okay, to LHS is equal in the both equations. So I might say that, okay, we must have this one, but this must be proved, and this is proved by many experimentalists, like in part of 10 to the power 12, that these two masses are indeed equal. So then Einstein said that, okay, if you have gravitational force, and if mass is falling, if mass is interacting with the gravitational force, then the equation of motion will not include the mass in that equations. This is a pure geometrical problem now. So from that, and using some more basic intuitions which Einstein had pretty much good, Einstein came to this conclusion that the gravity must have something related to space-time geometry. Space-time, because he earlier showed in the special theory of relativity that the space and times are exist as a simple quantity, as a single quantity, not two separate entities. Because of that simple relation between the Lorentz transformations, we can see that. So okay. So now, the above equations. Yeah. Just let me. Let's say check my notes now. So okay. The principle of equivalence. This suggests this, which suggests the above that the inertial mass and the gravitational mass are same, can be indeed represented as a local Poincare symmetry, which just says the simple thing. Like if we have some gravitational field any in this direction, then we can always find one simple free falling reference frame, which we can say okay, which will mimic the effect of this gravitational force. Because if our frame is freely falling in an if there is no gravitational field, if we have a free falling reference frame, then the initial frames will act like if it is falling under the gravitation forces. So the gravitation forces and the opposite inertial forces will cancel each other, and inside the frame that the only simple laws of SR will apply. And indeed, we can also see that with the simple consideration, we can also find the effect that the gravity will bend the light. If we only consider the special theory SR laws inside a freely falling laboratory. Yeah. So the Poincare symmetry says that okay, if we have a constant frame over here and we want to find the particular frame which will mimic the local gravitational field over inside this region, then we'll have to just do simple two transformations, which are what? Just first we have to align the origin of this frame with respect to this frame, which we can generally do by translation, and then to align the axis generally by translation, and then we have to just do a Lorentz transformation. If I look toward the Lorentz transformation from a different viewpoint, then I can say that the Lorentz transformation is just a rotation between the space and time axis. Just like the rotation moves the like if we are rotating our coordinate system in the simple rotation term, then we can say okay, I'm just moving my in a reference frame. The same is done by the Lorentz transformation. It just moves your coded axis, but it doesn't move your coded axis like the simple rotation does. With like every axis has been moved in anti-clockwise direction, but it does something miraculous that it moves your axis inside like toward the speed of light, like that toward the constant c equal to one axis, which must lie at the 45-degree angle for both x and t. So there are your new coordinate transformation. So we can consider the Lorentz transformation as just a simple coordinate rotation transformation between the time and the space axis. So let me introduce the notion of four vector, which as we all have been somewhat accustomed to. Like I can say the time and the spatial coordinates are considered as a four vector. A four vector is just because we'll consider the normal position as a three vector, and now we're including time also. So it's just a four vector. And to represent four vector, we always use these Greek symbols. And to represent simple vector, we always use IJK. This is the normal Latin symbols. So yeah. Okay, now we know from the Lagrangian field theory that we generally deal with. We will have something, a dynamical variable, and in the field theory, we'll generally have a field, and we'll have some Lagrangian density, which depend on the field and their spatial derivative or time derivative. Because yeah, if I'm using mu here to represent that, it can also represent on the spatial as well as temporal parts of the field. The temporal derivative is also included. And then the equation of motion are just generally given by the EL equations, which minimizes the action. And here the action is given by this q is just the generalized coordinates. For the field theory, okay. For the field theory, the EL equations are similar to which we have in the simple Lagrange for the classical dynamics. It's just given by this. And using this equation, we can reduce the dynamics of our field. So it's just a basic intro. Now, if we combine the Lorentz transformation, which is generally represented by this symbol, and translation, we will get we will call these like these transformations will form a group, which we will call the simple Poincare group, named after the German mathematician Henry Poincare. Yeah, I guess he is German. He was German. Okay. Yeah. As above, I have shown that these transformations can be that the principle of equivalence can be shown as a symmetry group. Principle of equivalence can be shown as being represented by this Poincare group. As above, I have shown that any gravitational field, any local gravitational field can be uh, yeah is locally equivalent to having a freely falling laboratory. I've been always using like a local. Yeah, the local word is important. Also in a locals in a local like yeah. If we have gravitational field, then only we can say that in a very small region, like a locally, we can represent that gravitational field as a simple freely falling body. Because if I wanted to do the same with that, like in a much bigger region, then I can't do that. Because then the stress and the strains from the gravitational field, like then we can say that okay, no, we are inside in the gravitational field. We are not just in a freely falling laboratory, because we can use like for a much extended laboratory, we will have some stress and strain that will deform our laboratory in some sense. Deformation of laboratory due to stress and strains of gravitational force. Yeah. Stress and strains are due to because the gravitational force depends on the distance, as we know it. So the difference between the gravitational forces at this point and this point will affect our laboratory, and we can deduce that no, we are inside a gravitational field, not just a simple freely falling body. So the local word is important here to show that locally we can do that. Like if I consider my laboratory too small, that the effects of gravitational field can are very less, I can say, are very minimal. So in that case, we can do that. Now, just for a matter of convention, this is my simple metric, and the metric signature I will use here is this simple metric, and the metric is diagonal. This is just to represent the the line element in any in my Minkowski space, the space for the Lorentz transformations generally goes by the name of M4, which is Minkowski four-dimensional space-time. Minkowski was the teacher of Einstein who pointed out that space and time can be thought as the space and time forms the four-dimension space. It's just a mathematical convention. So now I'll begin by the Poincare symmetry and finding the group generators of this Poincare group. Okay. Let us consider that we have a reference frame M4 and having some coordinates assigned to it, and we have a reference frame that assign these coordinates in that M4. And M4 will say that okay, the infinitesimal element between 2 points in my space between P and Q plus dx will be given by this simple metric, this simple line element. Now, if I have another reference frame in the same Minkowski space, then he'll represent the same line element using his different coordinate systems and his different metric. That the new metric will be represented by this. Here the repeating index is summed over, so no need to worry that we have two similar indexes. This is the simple Einstein convention applied here. So now what the principle of the equivalence of reference frame says that the form of our metric the form of metric do not change. Okay, I'm mistaken. The coordinate system will also be represented by dashes because we are in a new reference frame. Let us call this S and this one is S dash. So from the similarity of metric line element, I have to use different indices now because we're writing it together and we might not cancel them out. Okay, so the new reference frame which we have considered is inertial if the form of the metric tensor doesn't change its form. Then we have to say that the metric do not changes its form. The new metric assigned by this new reference frame is again the similar metric which has been assigned by the old reference frame. Now I'll present the two notions for a form variation of a field. Which of a field fx represented by the new fx. It's just that if f dash x is the new field in the new coordinate or we apply some transformations, then it's just the difference between the new and the old at the when we are evaluating at the same point x. And we can also have the total variation of a field which we will call del fx. Now let us consider that if we can relate our x and x dash by a small infinitesimal number, then I can see that my the variation of these field, this can be represented as simple del the form variation of the field plus this. This comes from this. If you Taylor expand this equation using this, and we will use this formula to get this one. I arrive at this by using the other two equations. One thing is important here: the form variation and the differential are commuting operators. The coordinate transformations x to x dash, which do not changes, which do not changes the form of the metric are known as isometric group of the space. So in our example, in our case, the space is Minkowski 4, and the isometric group is known as the global Poincare transformation. Isometric group of the four-dimensional Minkowski space is known as global Poincare transformation, represented by P1 and 3. 1 and 3 because of we have one temporal and three spatial coordinates. I have used here global Poincare transformation, so there must also be something called local Poincare transformation. In the above example of the equivalence of the principle of equivalence when considered geometrically, I said that if we have any gravitation field, then it can be mimicked by a local freely falling reference frame, which can be constructed from a constant reference frame by two motions of translation plus Lorentz rotations. If we have no gravitation field, let us say, if you have no gravitation field, then these transformations will not depend on the position we are having because if we have a varying gravitation field, for a varying gravitation field, gravitation field, then this frame will locally depend on the position of the gravitation field that we wanted to mimic. Then in some sense this frame will depend on the position x. Then we will say that these transformations that we are doing with this are called a local Poincare transformation. And if we have a constant gravitation field, then we can say that, or no gravitation field, and these transformations are called as global Poincare transformations. Yeah. Also we know that if the isometry of a space forms a group, then the generators of that groups are known as scaling vector field. Generators of isometric group are scaling scaling vector fields. So now let us find out for the infinitesimal Poincare transformations. Let us consider a coordinate transformation in which x mu changes to x plus mu, which we can represent by our old coordinate plus some infinitesimal parameter. Now both the metrics are related. We can relate the metric equation above. This this metric obviously depend on the position. Let us take the for this present case that the metric depend on the positions, but we know that it doesn't depend because it's just a simple diagonal matrix. And you wanted to consider the transformation which changes the form, which do not change the form of the metric, but we can generalize this to some position dependent metric also. Now we can use the simple equation into this, and we can do some basic mathematical algebra, tensor algebra, and we will reach out and we will reach finally this equation. Now, as we said that the form of the metric will not change, then we can say that this equation got to be zero, which is our Kelling equation. Now for the parameter, okay, I don't know the name of this parameter, but yeah, it's some Greek symbol. I can expand it in the power series of x. And by using this above equation, we okay here this epsilon naught and omega are constants, and constant parameters. And using the above Kelling equation, we reach to the result omega mean is equal to zero, and eta mu is some arbitrary parameter, and all the other parameter of higher order will cancel out. Now we can write the form for the infinitesimal Poincare transformation as has been determined by the two parameters, epsilon naught and omega. Here, this epsilon naught is simply represent the translation operator. The translation, and this omega are just the generator of the Lorentz transformations. From this equation, we know that omega is the antisymmetric matrix in 4 dimensions. So it has six parameters, six independent parameters. Which we can subdivide using say that okay, 3 for simple coordinate transformation, coordinate rotations, and 3 for space-time rotations, space-time Lorentz rotations. So on total, we can see that and the translation into the 4 parameters, because we can have translation in all the 4 dimensions of 3 spatial and 1 temporal. So Poincare group or these Poincare transformation forms a group which we call Poincare group. Poincare transformation form a 10 parameter Poincare group. Which is represented in here. Now I can also do the simple thing. If I represent the Poincare transformation using some T, and for the Lorentz transformation, I will use this Vedic symbol, which we generally found in many textbooks. So if I apply the two consecutive Poincare transformations, which I, which I can do, also I can represent a single one Poincare transformation using this above formula. It's just simple a plus lambda x. I'm not using the components here because that is already understood. So applying the two consecutive transformation will give me a simple result. And now I can find the inverse of this transformation from above formula, because I know that the inverse transformation and the transformation got to give me the identity transformation, and which is nothing but simple 0 1, which is just represented by the identity. And from the above consideration, using this formula, we can reach out that the inverse of the simple transformation is just given by this. I can call it the inverse transformation, inverse of the simple Poincare transformation is just given by this formula. Now I will find out the Lie algebra and the representations of Poincare transformations. When we want to find out how the Poincare group will act on the field, then we have to know its generators and the Lie algebra. Lie algebra and its representation. First, why do we need to have representation of a group? Because group connect on like group connect on scalars also, on multi-component objects also, like for example vectors or matrices. It can also act on. It connect on tensors also. Scalar vectors are just forms of tensor. So just like rotation group, we can find out the its metric representation, because when it then how we will represent, it's just that we if we wanted to represent the effect of this of the rotation group on some vector, and vector we can arrange it as a three component object. Then we have to find out the metric representation for the rotation. In just the similar ways, group connect on different objects, and for each of them we will have to find out its representation. Now let us consider a field phi x, which is scalar with respect to Poincare transformation. I'll show the representation here. I'll show the transformation again, which is scalar with respect to above transformation. That it doesn't change its form under the above transformation. Then, as a consequence, I can find out the form variance of my transformation is given by here. I have employed the above equation, which we have already found out that the variation and the total variation of the field is equal to the form variation plus its derivative. And we know that the for the scalar this tends to zero. So from our equation we get was this. Now I can represent the above equation in somewhat different fashion. Here I can show that these two are equivalent. And for that I can just say that okay, for P mu I'll call the derivative differential operator as a simple P mu, and for the M mu we can say that this is equal to in this pair, and these both the generators are the simple killing vector fields. You can see that. And if my mu and nu run over only spatial coordinates, then this simply reduced to my simple rotation operators, the angular momentum operators, which we have generally seen in quantum mechanics in different form in classical mechanics also. And if I have this the also the temporal components plus spatial components, then this will represent the generators for the simple Lorentz transformations. You can see from this how this equation will follow. It's a simple mathematical calculation which can be done. Now these two operators we can find the real algebra, which I will write down. In this equation, these two terms will repeat with just lambda changes to rho. In this equation, this last leave bracket just simply show that the two differential operators commute. Like we have already known, is these doing this twice is the same thing. Finding this relation might be tricky, so we'll take them arbitrary field and we'll just add the both the bracket and we'll just open the commutator, and then we can see that this will follow. Now for the arbitrary field phi, the generators will have the form. Therefore, this condition, I can also say that this might be the definition for L mu nu. And if you have the y arbitrary field, then we also have to include the spin operator also, spin part of this generator. This, the simple generators can be also found from the induced representation of group, which I won't dwell further because I don't have the subject knowledge. Now I can consider the invariance of actions in some conservation laws, which follows from the above equations. The invariance of theory under some transformation can be expressed in terms of some restriction on the Lagrangian. That because we know that the whole expression for the equation of motion and evolution of a theory can be found from the Lagrangian, then so the invariance must have some conditions, must enforce some condition in the form of the Lagrangian. I will only write this equation directly, but mathematics can be followed. In this equation, this dash is simply just the derivative of phi with respect to x here. I just use this shorthand convention. The first identity here can be considered as the condition for the Lorentz invariance. And the second constraint can be shown as the condition for translation invariance. Now, if I can write the infinitesimal change in my action when we do these transformations, this is just good old Lagrangian dependent on the fields and the coordinate derivatives. Now, after this simple Poincare transformation or any other transformation, the form of the Lagrangian will change. The form of the action will also change. This omega represents the space-time region over which this integration has been done. Space and region might be also different because of the transformation we are changing our code after the coded transformation. So whenever I can share that under the Corbo coded transformation, the action is invariant, then this is in general represented by this notion. Here, the form invariance of Lagrangian is nothing but simple the change in the. Now, employing these equations, I can write this above equation in much more general and simpler form. We have always seen this general constraint forms written in generally field theories where we want to represent some conserved equations or conserved currents. Here the J mu is simply the definition of J mu. This equation, this change in the Lagrangian with respect to the field are generally given by the Euler-Lagrange equations, which we have seen earlier. So I'll write them again. So to find out so whenever we say that this equation follows the equation of motion, then we will put this completely equal to zero because these are nothing but good old Euler-Lagrange equations for the field for a dynamical variable phi. Now using the above the invariance conditions will read on the differential on the conservation laws. Invariance will lead to conservation laws, and we can show that this will goes to zero because here I can see that if my if this follows the equation of motion, the En equation, then this will turn out to be zero. And delta L is always zero because the invariant of actions under the simple Fourier transformation. Then I can say that this the divergence of J menu goes has to be zero, which we can represent using the definition of J menu in these conditions, which we can call as conserved currents. J mu can be represented by using the omegas. Here, T menu represent energy momentum tensor, and M menu lemma represents the angular momentum tensor. Which we can be written in more general form. This is just a canonical delta function which vanishes for different indices and will give one when the both indices are same. This is the form of T menu which we have seen earlier also in field theories. And for the angular value tensor, this will comes out. This will also include the spin part also. As is called it as a spin tensor, which we can write as now one thing is important here. The canonical energy value tensor is not generally symmetric, which we always thought that it has to be. T menu is not symmetric generally. In general, but in some cases it might be. In the above equation, we can see that from the conserved equation, the omegas and the epsilons are constant. So this will simply reduce to the conserved equations for the energy value tensor and the angular value tensor. Where the divergence of the angular value tensor and these both vanishes. This is nothing but a type of a Noether's example of the Noether's theorem, which simply asserts that for the each parameter of a continuous symmetry in the Lagrangian, for each parameter of continuous symmetry in Lagrangian, there correspond a differential conserved current. And the integral over space, the free space of the null component of the current will define the related charges. That I won't go in much detail. And I would like to end my lecture here. And I just wanted to thank for this opportunity to speak, and also my friend Akash for providing the the, the screen and the tab also. And thank you once again for hearing me. Thanks. Any questions? So if you might ask. Okay then, thanks.